Hello, we will discuss directed graphs in this lecture. A directed graph is like a graph except we have directions on the edges. You will see definitions and results that are analogous to graphs, but some important differences will be noted. We will also relate directed graphs to undirected graphs by talking about their underlying graphs. Let's get started. We begin with some definitions. A directed graph, or digraph, consists of a set of nodes n and a set of arcs a, and these arcs are ordered pairs of nodes. In this example, we have a directed graph with 5 nodes and 8 arcs. Note that since the arcs are ordered, AB is not the same as BA. Now for an arc UV, U is called the tail and V is called the head. And when we draw this arc, we represent it as an arrow pointing from U to V. Now in graphs, we have the degree of a vertex. In digraphs, we have two types of degrees for a node. The out degree of V is the number of arcs whose tail is V, which is denoted by D of V. The in degree of V is the number of arcs whose head is V, and this is denoted by D of V bar. In this example, we see that the node B has exactly one arc coming out of it, that is the arc BE, so the out degree is 1. There are 3 arcs that goes into B, AB, CB, and DB, so the in degree is 3. We have analogous definitions for walks, paths, and cycles for directed graphs as well, but now we must follow the directions of the arc from tail to head. A directed walk or diwalk is a sequence of nodes v1 to vk such that vi plus 1 are arcs. Once again, there are no restrictions on the repetition of nodes or arcs. In this example, we have a red directed walk that goes from A to eventually E. A directed path or dipath is a directed walk where all the nodes are distinct, so we do not repeat any nodes or arcs. Here we have a green directed path going from A all the way around to C. A directed cycle or dicycle is a directed walk from V1 to Vk and then back to V1 where all the nodes are distinct and k is at least 3. Here we have a short dicycle going from B to E to D and then back to B. Note that some people will allow k to be at least 2, meaning if there is an arc from A to B and B to A, they will count that as a dicycle of length 2. We will stick to k at least 3 for now. We now move on to the important topic of cuts. Cuts in digraphs are similar to the way cuts are defined in graphs, but now we only consider arcs that go in the same direction. For a subset of nodes S, the cut induced by S is the set of all arcs whose tails are in S and heads are not in S. The notation here is delta of S, which is all the arcs UV where U is in S and V is not in S. This might look exactly the same as the definition of a cut in an undirected graph, but now with directions, there may be arcs that seem to cross a cut but are not actually in the cut. If we want to talk about arcs that go into S, then we will write delta of S bar, which are the arcs UV where U is not in S and V is in S. This notation makes sense because the set of all the arcs that go into S is the same as the set of all the arcs that go out of the complement of S. In this example, suppose S is equal to A, C, and D. The blue line puts A, C, and D on one side and B and E on the other side. There seems to be 4 arcs that cross this cut, but only 3 of them are in delta of S. Those are AB, CB, and DB. These are the arcs that go out of S. There is one arc that goes into S that is ED, so that is in delta of S bar. If we have 2 nodes S and T where S is in big S and T is not in S, then delta of S is an ST cut. Similar to graphs, there is a close relation between paths and cuts. In this case, we have this proposition. There exists an ST dipath if and only if every ST cut is non-empty. We will write the full proof here to get you used to the idea of proofs in digraphs. We begin with the forward direction of the proof. We assume that there is an ST dipath, so let V1 to Vk be this dipath, and let delta of S be any ST cut. The goal is to show that there is some arc in delta of S. Intuitively, S and T are on different sides of the cut, so if we want to go from S to T, we must cross the cut somewhere. To make the proof more formal, look at the diagram, and let's pick the last possible node in the path that is still in S. The next node is not in S, so we have found our arc in the cut. Now let's write down the proof. Since V1 is in S and Vk is not in S, there exists a largest index I such that Vi is in S and I is less than k, meaning Vi is not the very last node, which is T. Then Vi plus 1 is not in S. So Vi being in S and Vi plus 1 being not in S implies that Vi plus 1 is in delta of S. So delta of S is non-empty. This completes this half of the proof. For the other direction of the proof, we're going to assume that every ST cut is non-empty, and then try to find an ST dipath. One possible way of finding this dipath is by building it iteratively. We can start with the node S and look at the cut induced by this one node only. By assumption, this cut is non-empty, so there must be an arc from S to another node. We then look at the cut induced by these two nodes, which by assumption is non-empty. So there is another arc that goes from one of these two nodes to a third node. And then we can repeat this process until we reach T, in which case we have found an ST dipath. Now writing this iterative proof formally is not easy, so let's think about this from another angle. We can ask, suppose we never reach T, then what went wrong? Well, we can collect all the nodes that can be reached from S through a dipath. If this does not include T, then the collection of all such nodes must induce an empty cut, for otherwise we can find additional nodes to reach from S. Now let's write down the proof. Let S be the set of all nodes V such that an SV dipath exists in the digraph. If T is in S, then an ST dipath exists and we are done. Otherwise, T is not in S, so delta of S is an ST cut. So by assumption, there must exist an arc UV that is in delta of S, meaning U is in S and V is not in S. Now since U is in S, there must exist an SU dipath, let's call it P. Then P, along with the arc UV, is an SV dipath. Therefore, V must be in S. This contradicts the fact that V is actually not in S, and this completes the proof of our proposition. Finally, we will relate digraphs to graphs by talking about their underlying graphs. Informally, the underlying graph of a digraph is obtained by removing the directions on the arcs to get edges. We see a quick example here. Now, there are a few terms from graphs that we will apply to digraphs, but in reality, we are really connecting them to the underlying graphs of these digraphs. The first term is about connectedness. A digraph is connected if its underlying graph is connected. Note that even if a digraph is connected, there might not be a dipath between every ordered pair of vertices. For example, suppose you have a digraph that consists of just an arc from U to V. Then, in this digraph, there is no dipath from V to U. As an aside, if there is a dipath between every ordered pair of vertices, then the digraph is called strongly connected. We won't be using this term in this course. The notion of a spanning tree can be transferred into digraphs as well. A spanning tree in the digraph corresponds to a spanning tree in the underlying graph. Here in my small example, I have drawn a spanning tree in my digraph. And finally, a cycle in a digraph corresponds to a cycle in the underlying graph. Here is an example on our digraph. Note that a cycle is not necessarily a directed cycle. A couple of terms that we will see in the near future. Suppose we take a cycle in an undirected graph. We can imagine traveling on it in two different directions. If we fix one direction, then this cycle turns into a directed cycle. Then, if we compare this directed cycle with the original cycle in the digraph, we can then call those arcs that match the direction the forward arcs, and those arcs that run in the opposite direction the backward arcs. And that concludes our short overview of directed graphs. Next time, we will start discussing the transshipment problem.